Alright, welcome back. So, any questions come up? Either this is a remarkable class and people have totally got this nailed, or I've done such a horrible job explaining this that you don't even know where to begin asking questions, or maybe people are just not wanting to ask questions and you're going to try to figure it out later. This is tricky stuff, right? Pulse width modulation is a simple concept, but actually generating these kind of waveforms in code can be tricky. But this is something that we do a fair amount at a low level. And it's not just pulse width modulated output. If you want to send serial information across a wire, right, you need to generate high and low signals, and you need to change the appearance of that signal, right? Sometimes we do something called well, it's another version of pulse width modulation, but you know, sometimes what we do is you know, we send a pulse of signals for a short period, and then we send a pulse of signals for a long period, and then we send a pulse for a short period, right? And this represents a 0 and a 1 and a 0. If you have a TV remote control, right, it's probably using something like this to send infrared signals that code up 0s and 1s. So you hit the 5 button and there's a code, hex 72 maybe, right? 8 bits that need to get transmitted to the TV's receiver, and it does that by generating a signal, typically 40 kilohertz, and it generates a short burst or a long burst to code up 1s and 0s. Now if you want to do that from a microprocessor, right, there's sometimes hardware support inside a chip that will let you specify this behavior, but you can do this by hand, right? You can just put an output high, wait the amount of time corresponding to a 40 kilohertz signal, and then send it low, and do that, you know, 4 times if you're trying to send a logic 0, or 12 times if you're trying to send a logic 1. Put a break in between so you can separate your bits, and you can send information, right? This is how this stuff works. And so understanding what's going on is one part of the challenge, and then being able to envision an algorithm for generating these kinds of outputs is another challenge, and then being able to write it in code is a third challenge, and then being able to simulate it and analyze the results of that simulation is yet another challenge. Okay, so these are all the things going into Lab 5 and into these discussions we're having. All right, so let's go on with timers. So we've been talking about timer 0. Okay, timer 0 has the following characteristics. It can be 8 bits or 16 bits. And it can have an optional prescaler. Now mostly we've been playing with no prescaler and with plain old 8 bits. But remember, there's this timer 0 register. And TMR0 is not really what this register is called, but it means one of two things. In 8-bit mode, the register we use is timer 0L. In 16-bit mode, the register we use is this composite of timer 0H and timer 0L. So if we want a long period and we want to store 1,000, we want to set our system up to overflow at 1,000, The overflow value is 65,536. Take away 1,000. We should initialize this composite 16-bit register to this value, 64,536. All right, so how do we do that? So bring up your hex calculator, 64,536. Put that into hex, and it's FC18. So all you got to do is put an 18 into timer 0L and put an FC into timer 0H. And that will initialize the system to 64,536 as your initial value. And then every time that the instruction cycle clock ticks, this will get incremented. After 1,000 increments, it will be equal to this, which is the overflow value for a 16-bit number, and you get your interrupt request. All right, there's an important detail about dealing with 16-bit registers, and this comes up in a few contexts. It's not super critical, and it's not going to show up in any of the labs we're doing, but it can show up in some contexts, and it can be a big difference. So there's a rule. When you have a 16-bit register like this, you want to write the high part first, and then write the low part. So if I wanted to load this value into timer 0H, it's very important that I write FC into timer 0H and then write an 18 into timer 0L. You got to do it in that order. When you're reading, you want to read the low part first, and then read the high part. So if I wanted to know the current value of this timer register and I wanted to save it in a pair of file registers, it's very important that I read the low byte first and then read the high byte. Okay, that's just something to know. And page 102 of the data sheet will explain that to you, but it would take us about 10 minutes to go through the explanation, and I'm not sure it would actually make sense. But it has to do with the fact that you're trying to read or write a register that's changing, right? And if this is incrementing every instruction, to write this 16-bit value into here, I have to move 18 into W, move that into a timer low, move FC into W, move that into timer high. That's 4 instructions. During those 4 instructions, this register will be changing value. And if the low part happens to roll over while I'm going through those 4 instructions, I can end up with bogus values. So there's hardware support. You can see it on page 102 of the data sheet that helps you avoid this if you stick with these rules. When you're writing a 16-bit register, write the high byte first. When you're reading a 16-bit register, read the low byte first. Okay, that's just one of those things to know. All right, other timers. So, timer 1 is almost the same as timer 0. The main difference is it doesn't have as many prescalers. We can set a prescaler 1 to 1, which is no prescaler at all, 1 to 2, 1 to 4, 1 to 8. You turn it on with bit 0. You set this bit to a 0, bit 1 to say I want to go from the instruction clock, that's the system clock divided by 4. Okay. I don't think we need to worry about the oscillator bit. We don't need to worry about the external sync bit. So it's basically another timer. And it works as a 16-bit timer. So 16-bit counter. Timer 3, did I actually put it in here? I did not. Timer 3, same thing. It's a 16-bit register. It has a prescaler from 1 to 1 to 1 to 8. You turn it on with bit 0. You choose your source with bit 1. Very similar to timer 1. Okay. Timer 2 is the real oddball. So there's a few significant differences for timer 2. Number 1, it's only an 8-bit counter. Does not have a 16-bit mode available. So that's one difference. Number 2, it has a prescaler and a postscaler. Okay, the prescaler can be anything from can be 1 to 1, 1 to 4, or 1 to 16. The postscaler can be anything from 1 to 1 through 1 to 16. And if you know how the prescaler works, the combination of these is basically the same effect. You multiply these together. If I set a prescaler 1 to 16 and a postscaler 1 to 16, it's basically saying every 256 instruction cycle ticks, go ahead and increment my register, timer 2. Right, 1 to 1, this will increment every instruction cycle. 1 to 4, it would increment every 4 instruction cycles. 1 to 1 and 1 to 4, right, the effect is it's incrementing every 4 instruction cycles. So you basically multiply these together to find out how much the instruction cycle clock is being effectively slowed down. Okay, that's not the real magic of timer 2. The really cool part about timer 2 is timer 2 increments, right? And when it overflows, it okay, the other timers increment, and when they overflow, they generate an interrupt. Timer 2 increments until it's equal to another register, which is called PR2. That's the period register. And when it's equal to the period register, it interrupts and resets timer 2. Okay, what does this matter? What does this mean? Let's look at timer 0. And let's suppose we're in 8-bit mode. And let's suppose I initialize this to 246 decimal. Okay, 10 ticks later, this is 256, which is the same as 0, and we get an interrupt. Okay, all things being equal, the next interrupt is not going to occur after another 10 ticks. It's going to take 256 ticks till it gets back to 256, resets to 0, and generates an interrupt. If I want it to interrupt repeatedly after 10 ticks, what I need to do in this interrupt code is reset this to 246. And then after 10 more ticks, it overflows. Right? But you have to write software that says when you get an interrupt, let's reload this magic value into the timer register. You don't have to do that with timer 2. So timer 2 starts off at 0, but I have this period register, PR2. Let's say I set this to 10. Okay? After 10 ticks, timer 2 is incremented to 10. That's equal to the period register. It gets reset to 0, and we get an interrupt. After 10 more instructions, this 0 will increment to 10. That's equal to the period register. It'll reset to 0 and get an interrupt. I don't have to do anything in software. Right? All I have to do is set my period register, and this will automatically generate an interrupt, in this case every 10 ticks. Let's see, can we use a strategy for timer 0 in Lab 5? Well, I don't know what strategy you mean, because this is only for timer 2. But you do something like this in Lab 5. If you're using timer 0, you have to continually reload whatever value you want it to start at. which I think is 0 in the demo code. Or you could use timer 2 in the lab if you want. It may be a little more complicated because of the period register, but yeah, either of those would be fine. Alright, so timer 2 is nice because you set it up and you never have to think about it. It's just going to generate an interrupt every certain amount of time, and you can do whatever you want in the interrupt and not even think about timers anymore. Okay, it's just going to keep doing its thing. And it's only 8 bits, but right, we can go up to a 256 combination scalar, and we can dial it in fairly precisely. We have 1-to-1 all the way up to 1-to-16 available for our post scalar. So that's timer 2. Okay, it's always 8 bits. It counts up, but it overflows at the point where it matches PR2. That's the big differences from the other timers. Alright, why do they do this? Other than the fact that sometimes it's nice not to have to worry about resetting your timer register. This goes into what's called the ECCP subsystem, Enhanced Capture Compare Pulse Width Modulation module. And this is another thing that most modern processors have, something to support these kinds of functions. So PWM is the one we want to talk about. There is hardware support inside the PIC chip to automatically generate pulse width modulated signals. Now, I don't want you to use this for Lab 5. Lab 5, you have to generate these signals by hand, okay, the way we've been talking. But independent of Lab 5, I want to go through this system. And basically, we can pick a duty cycle and have the PIC automatically generate an output with that duty cycle. And we do it using timer 2. We set timer 2 to interrupt, at whatever period we want the output waveform to have. And the duty cycle is controlled by using this register, CCPR1L and CCPR1H. So let's go down to PWM mode. And there's way more stuff in here than you want to think about too seriously, including logarithms, which is always good. But here's the basic deal, right? Whatever value you set in PR2, that's effectively the period of the waveform. Whatever value you set in CCPR1L is effectively the duty cycle. It's the part of PR2 during which your output is high. So if you want to generate a pulse width modulated signal using the subsystem, you set up timer 2 for the period you're interested in, and then you just load a value into CCPR1L, and the system will have the following duty cycle: CCPR1L divided by whatever the PR2 value is. Alright, we're not going to play with this in this class. Normally we use these to actually drive around a little car with variable speed. We're not going to play with this in this course. But if you do embedded systems down the road, you'll definitely encounter this, and I just want you to know that there is a system inside the chip for actually generating these pulse width modulated signals. And when you set this up, so it's a simple 9-step process to set it up. But let's take a look at the configuration register. So if you haven't noticed yet, right, all of these systems that we're talking about, there's always a con register. There's int con, there's T0 con, there's CCP1 con, right? These are the control registers for whatever subsystem. So this register, it's 7 bits. And these 2 bits here, bits 3 and 2, well, 3 through 0, basically say what do we want the subsystem to do. If we want to generate pulse width modulation, typically we'll set those 4 bits to 1100. This will be pulse width modulated mode. P1A and P1C are active high. And then in that case, that affects what these two most significant bits do. So the behavior of bits 7 and 6 depend on the behavior of bits 3 and 2. If bits 3 and 2 are either 0, 0, 0, 1, or 1, 0, then this is a capture or compare operation. But if bits 3 and 2 are 1, 1, pulse width modulated output, then these two bits control other aspects of that PWM generation. And the one we typically use is a single output on pin P1A. So we would set these two bits to 0, 0. And then we generate pulse width modulated output on pin P1A. Well, what is pin P1A? P1A is pin 18, that's also RB3. So bit 3 of port B is the PWM generated system output, which is why it's wired to that little motor on the GUI interface. Alright, so we'll skip over lots of detail along with half bridge and full bridge output discussions, and these are things you'll definitely get into if you're electrical engineering. You'll learn all about these, and these are related to the realities of physical stuff versus simulation. Right? The way I've described pulse width modulated output to control a motor speed is really straightforward on paper. It's very, very complex in the physical world. And so those are what all these other bits refer to, is ways to deal with that. Alright, that's all I have to say on PWM support in the hardware. Questions? Let's back up a minute. Are people feeling pretty confident about Lab 5? Or confident enough to make a good start on it?
Good enough to make a start on it.
Okay. The biggest challenge in all of these is always getting started.
I would guess some people need to get input before they can formulate questions.
Right. Yeah, and once you start writing code and looking at outputs, then if it's not making sense, that's when it'll really jump out at you.
Do you think you would go through the flow of that program that you built just one more time?
Oh yeah, and I wanted to go through some pseudocode for Lab 5 also. But let's look at that program again. So you know the interrupt setup, you know the interrupt vector, the reset vector. That's all just stuff that happens in the beginning. So the main program is doing what? It's reading port A, deciding what to set this variable high part to, either 1 or 3, depending on what duty cycle we want. Alright, so the interrupt code. When an interrupt occurs, basically increment our counter to say how far are we into the cycle. If we're all the way through, if the counter is equal to 4, we're done with this waveform. We're going to go back and start a new waveform. So come down here, set the output high, clear the counter. That's one possibility. Second possibility is we increment the counter and it's equal to this variable high part, meaning that the output signal has been high as long as it's supposed to be, in which case we need to now set the output low. That's the second possibility. Third possibility is nothing special has happened. We simply increment the counter and we're done. So let's look at this with respect to Lab 5. So RB0 is supposed to be 2 hertz. which is every 512 milliseconds. And we're going to drive everything with milliseconds. The sample code sets up interrupts to occur every millisecond, so I'm just going to put everything in terms of milliseconds. So this 0.256 seconds, 256 milliseconds. So toggle every 256, which means the period is 512. All right. RA0 is supposed to be 250 hertz, which means a 4 millisecond period. And we want to go RA0 from 100, 75, 50, 25, 0, and back up. Alright, so RA0, 2 hertz signal, RA0, 250 hertz signal with a changing duty cycle. And I'm just going to go from 100 to 75, 50, 25, 0, 25, 50, 75, and back to 100. Technically, if you read the lab, it looks like after you're at 100% maximum power, you should go back to step 1 and stay at 100% maximum power another step. I'm not going to ask you to do that. If you do it, it's fine. But let's just go 175, 50, 25, 0, 25, 50, 75, 100, 75, 50, 25. Just go back and forth smoothly. All right. So everything is driven off of our interrupt code, right? We're going to do some sort of initialization. But again, let's have a count equals 0. Let's have a high part equal to, I don't know, I'll set it equal to 4 to start off at 100% duty cycle. And so what happens when we get our interrupt? We know that 1 millisecond has passed. Okay, so I'm going to make something called RB count. And I'm going to use that to control RB0. And I'm going to have something called RB value, or RB level, or RB out. And I'll bounce this between 1 and 0. So I'll start this at 0. I'll start this at, I don't know, I'll just start it at 1. Alright, so first thing I want to do, every time I get an interrupt, I'm going to increment RB count. That's going to count how long this signal has been in its current state. If it's equal to 0, what am I going to do? I'm going to toggle RB out. And I'm going to send RB out to RB0. Alright, every millisecond increment RB count. If it's equal to 0, it means it has incremented 256 times. Which, remember, for RB0, it's high for 256 milliseconds, it's low for 256. So I don't have to compare it to a period register that's 256, right? After 256 increments, it will go back to 0. That's when I should change RB0. So I'll toggle my RB out variable and I'll send that to RB0. Okay, that's the whole handling of RB0 in our interrupt code. That's the easier part. All right, second part. So this is, this is handling RB0. The second part, adjust power if needed. All right, so how do we do this? We need to adjust the power every what? Every half a second. Well, I can cheat and make life easy on myself because I know every half second RB0 is going to go from 0 to 1. Half second RB0 is going to go from 0 to 1. So I can simply adjust the power if needed. If RB0 just changed from 0 to 1. Alright, what can I look at in my file registers to tell me if RB0 just changed from a 0 to 1? What high-level if statement could I write? Just based on what I've got on this page so far. You can microphone or you can chat it to me if you want. But think of an if statement that will tell me that this has just happened. So what's the value of RB count when my output changes, when my output toggles? Yeah, it's going to be 0. It might be 1. It's always a fence post thing. But yeah, it's actually going to be 0. Right? So I'm going to increment RB count. It's going to go to 100 and 200 and 250 and 255. And if it's 255 and I get another interrupt, I'll increment it to 256, which is 0. I'll notice that it's 0. I'll toggle my output. So if I want to know, did my output just change, I can say if RB count is equal to 0. That tells me my output just changed. I also want to know, is my output high? Did it just change from low to high? So if RB count equals 0 and RB out is equal to 1, then adjust the power level. In other words, this if condition will be satisfied exactly every 512 milliseconds. And this is saying adjust the power level every 512 milliseconds. Alright, so how am I going to adjust the power level? Increment state. And well, I'll just stick with the plan that's here because it's easy. So if state is equal to 10, then set state equal to 1. So we'll initialize state equal to 1. And after half a second, I'll increment state, and if state's 10, I'll reset it to 1. Alright, well now if I'm going to do this high part count business to modulate RA0, I need to change high part based on my current state. So 100% duty cycle is state is equal to 1 or 9. So if state is 1 or 9, set my high part to 4, which means I should keep the signal on for the entire duration of the period. "75% duty cycle is at states 2 and 8, so if state equals 2 or 8, set my high part to 3. Alright, so if RB count is 0 or and RB out is 1, adjust the power level. Increment the state. If the state is 10, set it back to 1. And now adjust this high part based on the state. If it's 1 or 9, make the high part 4. If it's 2 or 8, make the high part 3. If it's 3 or 7, make it 2. If it's 2 or 6, make it 1. Sorry, if it's 4 or 6. And if it's 5, make it 0. So all I'm doing is translating the state into what power level do we want. And I'm setting this power level by setting this high part variable that we had in that sample code. Alright, so we'll rehash this in a minute, but let's move forward. Third and final piece of this is to generate RA0 output. So increment count if the count's equal to the high part, set RA0 low. Before we do that, I'm going to say if it doesn't matter. If count is equal to 4, which is our period, set RA0 equal to 1 and set count equal to 0. So this is what we were doing in the sample code. Each time we get an interrupt, increment our counter, which says how far are we into the waveform. If it's equal to the value for our duty cycle, right? If it's equal to the end of the high part of the waveform, set the output low. If it's equal to the period, set the output high, reset the count to 0. Anytime we change state, let's reset the count so that we start over with a fresh waveform. And then there's one other thing we have to do in here. Special cases. If the high part is equal to 0, that's a 0% duty cycle. Set RA0 equal to 0. And we're done. If the high part is 4, set RA0 equal to 1. That's a 100% duty cycle, and we're done. Otherwise, increment the count, see if you're equal to the high part, send the output low, see if you're equal to the period, reset the count, set the output high. Alright, so all of this could be your interrupt code. Right, lots of stuff happens in your interrupt. But it's 3 pieces. Alright, quick review. Adjust RB0 as appropriate. So you get an interrupt. First thing you do, adjust RB0. Increment your RB count. If it rolls over, toggle RB's output and send that to RB0. That's got RB0 going at a quarter second high, quarter second low. If RB count just rolled over and you just set the output high, it means you just passed this point in your waveform, which means a half second has passed. It's time to adjust the duty cycle. So increment the count. If it's equal to 10, roll it over, reset the count for RA's generation, and then set the high part for RA's generation based on the state you're in. Okay, this is your power adjustment schedule. And then manage your RA signal output which we did in the sample code. So count how far you are into the cycle. If you're equal to the value high part, send the output low. If you're equal to the period, send the output high, reset the count. Now how you do this is totally up to you. This is mostly pseudocode. Okay, I use a few opcodes like INCF, but this is a high-level picture of what you want your code to do. And this is what you want to scratch your head over, put on a piece of paper or a whiteboard, talk over with friends, ponder on a walk through the woods, whatever. This is what you want to be thinking about. Okay, not T0 con, int 0 IE, etc., right? Try to understand from an algorithmic point of view what you're trying to do. And then, once you've made peace with this and you're confident that, yeah, okay, I know this is going to do what I want, then code this. And there's a lot of ways to code this in assembly language. So, you know, how you're going to do this, you could do a series of if statements and just literally say if the state's equal to 1, do this. If the state's equal to 2, do that. If it's equal to 3, do that. You may find some tricks that let you, by doing logic operations, change a state into a setting for the high part. There's lots of options, right? The trick is when you're debugging your code, you want to be debugging, okay, if the state is 3 or 7, then high part should be equal to 2. That's all you want to be concentrating on. Hey, my state is 7, but high part didn't get set equal to 2. That's a very specific bug to try to track down. What you don't want to be thinking about when you're debugging your code is, my state just changed to 3, but my output signal is permanently high, and I don't know why that is, and my timer is not resetting when it interrupts, and my interrupt code is jumping to location 18 instead of location 8. Don't be thinking about those details, right? Figure this stuff out in a way that makes sense to you. Write it up in a way that's, you know, clean flowchart, pseudocode, whatever works for you, and then translate this into pick assembly language. And then if your program's not doing what you want it to do, your only question should be, does my pick assembly language do this, and this, and this, and this, and this, right? Not, should I make this a 2 or should I make it a 3, or should I be doing this before I do this, or should I be doing this after I do that, right? Figure out the algorithm first, make that one challenge, and then convert your algorithm into assembly language, let that be the second challenge. And that's a general recipe for all of this stuff, right? And it's just like in Engineering 250, you make a schematic, right? Well, you make a truth table, and then a schematic, and then a wiring diagram, and then you build your circuit. And when you're building your circuit, you don't want to be thinking about, is my truth table right? Alright, so question, what does count do? Count was this idea that RA0 is supposed to look, for example, like this. And we get interrupts periodically. So I'm marking those 1 millisecond intervals where interrupts are going to occur. So count is counting how far we are from the beginning of this waveform. So after the first interrupt, we're right here. I'm going to set count equal to 1. After a second interrupt, I'm going to increment count. It's going to be 2. That's going to tell me I'm 2 steps into my waveform. After a third interrupt, 3 milliseconds have passed. Count will be 3. That tells me I'm 1, 2, 3 milliseconds into my waveform. And if high part is equal to 3, that says I want my waveform to be high for 3 milliseconds. So by comparing count to high part, I know, hey, enough time has passed that now my output should go low. So I set output low. And then after one more interrupt, count will be 4. That tells me 4 milliseconds have passed since the start of my waveform. That's my period. Now I'm ready to start repeating this pattern again. So reset count to 0, set the output high. We're in exactly the same state we were when we were back here 4 milliseconds earlier. This stuff will make your brain happy, and it will give you crazy dreams, which is always like bonus, right? If you come out of a class and you start having bizarre dreams at night, that's like a good class. This is breaking apart the world into different size, different shaped pieces and putting them back together again. It's something that our brains love doing, right? It's why we've gotten to where we are as a species. This is, you know, the essence of chess and philosophy and all this other stuff. It's okay if it's confusing. It's good if it's confusing. If it's not confusing at all and never has been, you may be thinking about it at too high of a level. You may not be really getting down to the nuts and bolts. You may be glancing and saying, oh yeah, that makes sense. The more you dig into this, the more you actually start to understand it, the more confusing it's going to seem for a while. Okay, that's a positive sign. That's a good thing. It's a feeling you should welcome, because it tells you that you're really getting down to the nuts and bolts. And then as these things start falling into place and you start making timing diagrams and going through and pretending you're a computer and incrementing registers and so on, those confusions start to become less prevalent. And eventually, you know, you've got this to a point where you're feeling pretty comfortable, and then you code it up and you look at it in the simulator and you look at waveforms and you look at register values, and it'll really start to click. Or if something's not quite right, it'll really start to jump out at you, and you correct whatever the misunderstanding is, and things will start to click again. And seriously, it's like one of the best feelings in the world when you figure this stuff out, right? It's something we're wired to do. So don't be frustrated if this is all confusing, right? The goal is to get in there, start writing some code, start working with this stuff, see what it's doing, and the best way to make this work is to start with something and modify it, right? Look in the simulator, look at the logic analyzer output, see what it's doing, understand what it's doing, and then tweak it. Right, and you do that enough, you're an excellent programmer, you're an excellent electrical engineer. This is all win-win. All right, I'm going to cut it off there. I'm going to let you get to your labs a few minutes early. I will be in my office for until 3:50. I will post some homework. I'm thinking I might push the homework back one class, but let me see what the homework looks like and what we're ready for. But I'll post an announcement on Canvas letting you know the story with the homework. And I'll see you in my office. All right, thanks.